Hello everyone, I'm Samuel from Brookhaven National Lab. In this talk, I will present a work about a construction of a novel quantum machine learning architecture, which we call quantum non-short-term memory, and the results using this model. It is capable of modeling time series faster than its classical counterpart. This work is done in collaboration with Xinjie Yu and Leo Fang, also from BNL. First, let me give you a bit of motivation as for why we are interested in time series. It is a kind of sequential data that is commonly in machine learning community. For example, in natural language processing, the models need to process a significant amount of text strings. In physics, dynamical data are usually recorded in the sequential form, such as the time evolution of a quantum system. In addition, the forefront of reinforcement learning also depends on certain kinds of memory to keep track of the trajectory, which is crucial for the agent to make better decisions in later time steps. In light of this, our goal is to investigate machine learning architectures so as to predict time series more accurately. Given that the classical machine learning community has invested a lot of effort on this, it is natural to ask whether quantum computers can promise something better. So, to explain our architecture, we first refresh some basic ideas from classical machine learning. In machine learning, recurrent neural networks, the RNN, are designed to process sequential data. The general idea is that given the input x at a time step t, the output at a time t is fed back into the neural network to predict the next time step t plus 1. It means that the model can keep some form of the earlier information, that is, returning certain memory. However, the RNN suffers from some problems. For example, its performance goes down when the temporal dependence is too long, and it is very hard to train due to vanishing gradient. Non-short-term memory, LSTM, is a modified form of RNN to fix these issues. It processes the cell states to keep track of the long dependence and reduce the vanishing gradients problem. Inside each unit cell in time, there are a few neural networks W to process the input X and hidden state H. And their output is passed through some nonlinear activation function to operate with the cell state C. C and H are then passed to the next time step T plus 1. In order to perform quantum machine learning, we propose a quantum enhanced form of LSTM, with the classical neural networks W replaced by the variational quantum circuits. The VQC blue boxes, which I will explain in detail in the next slide. We keep all other components from LSTM as classical, including the cell state and nonlinear activation functions, so that we can still do fan-out and bypass the limitation of the non-cloning theorem in quantum physics. So now let us take a closer look at the VQC component in our QLSTM model. The variational quantum circuit used in this work consists of 3 parts. The first part is encoding, which is used to transform classical values into a quantum state. V1 to V4 are first transformed with arctangent function to generate rotation angles along different axes. The second is the learning part, which includes several CNOT gates to entangle the qubits and tunable parameters alpha, beta, and gamma subject to optimization. These dashed boxes can be repeated as needed to improve the result, at the cost of increasing the number of training parameters. Finally, the measurements are done in the poly Z basis to get expectation values, which are then further processed and passed to other classical components in the QLSTM architecture as mentioned earlier. To put all pieces together, the last question is how to train the quantum circuit parameters. To do so, we adopt the hybrid quantum classical paradigm, which is suitable for currently available NISQ devices. The idea is that the certain part of calculation are performed on the quantum computer, while the optimization procedure is carried out on the classical computer. With this framework, we can easily apply the optimization methods developed in the classical machine learning community. For very complex architectures such as ours, instead of training on real devices, we can also train the model using quantum simulation software like QLEX or other high-performance backend. Before, we report several different time series. The input to the model is the past 4 time step. The model is trained to predict the fifth value in a sliding window fashion. For example, given x1 to x4, we predict x5, and given x2 to x5, we predict x6, and so on. We use mean square error as the loss and RMS probe as the optimizer. To make a fair comparison with classical LSTM, we construct the classical neural networks such that they have about the same number of parameters as QLSTM does. The gradient calculation is based on the parameter shift rule, which can calculate the analytical gradient of quantum functions or quantum models. The proposed model can easily be integrated with other quantum or classical components. For the simplest time series, we first try the sine function, which is considered to be a very easy task. We take the first 2/3 of data points for training and the last 1/3 for testing. The orange curve is the ground truth, and the blue curves are predicted results from QLSTM in the top row and classical LSTM in the bottom row. Taken at different training apples 1, 15, 30, and 100. We observe that the QLSTM learns faster than the classical LSTM. Noted that after just one apple, QLSTM already picks up the correct oscillating frequency with a much reasonable amplitude. Also, the decay of its loss function is more monotonic than that of classical LSTM, which has strange spikes that are known in classical machine learning. Next, we increase the difficulty level from sine function to damped simple harmonic oscillation that obeys this second-order ordinary differential equation. Again, we observe that the QLSTM can capture the pattern faster than its classical counterpart after just a single apple. Also, notice that classical LSTM has a very hard time capturing the correct equilibrium 0 point, which QLSTM has no problem at the first apple. In the J2 function, we observe significantly better performance in QLSTM. We also notice that the loss values in QLSTM are more stable than the classical one without the spikes. Classical LSTM still struggles a bit at apple 30, while QLSTM is getting very close to the ground truth. We further test the QLSTM on a delayed quantum feedback setup. We observed consistent result as the previous ones. Note the local extrema is better captured by the QLSTM. In conclusion, the QLSTM learns faster than classical LSTM when the number of parameters are similar. And we also observe that the loss function decrease is more stable in the QLSTM. Third, the QLSTM captures local extrema and 0 point much better than the classical LSTM. Future direction may include first, study different data encoding methods to process different kinds of classical data or content data. Second, it is probably interesting to try implementing this scheme on the actual near-term quantum devices. Thank you.